Chapter 1, Digital Systems and Binary Numbers. Section 1.1, Digital Systems. A digital system is something where information can be represented with digits or discrete values or a countable number of values. Okay. Now, digital systems are designed to store and process, communicate information in a digital form. So one of the examples, of course, is a computer, and you can think about, if we're talking about these specific topics, store information. What do we have on a computer? We have like a hard drive or, um, a CD drive or a thumb drive, something of that nature. Processing, computers have, main memory, RAM memory, and they have a CPU. And basically, it goes through, and if you have a program that executes on the computer, what it will do is, you give it some information um, through the keyboard, let's say, do some calculations potentially, or process some data, and it'll display it on the output. And typically, that's done through the display. So when we talk about communicate information, that is either, I/O, input and output. There are, of course, other ways to communicate information, get information into the computer and get information out of the computer, besides just like the display. You also can print potentially if you want to do that, okay? Or use it to control some actions. So here's some other examples where digital systems are used, of course. Some images here. One of them that's used. Cars have progressed quite a lot and have very sophisticated computers in them now to process a lot of different information. And here's like an example of that. You also are used in control systems. Here's a simple example. You have some inflow of something, let's say water, and maybe this pump is controlling the outflow or the overflow. And if the level gets too high, it triggers this pump on and it pumps, let's say, whatever this fluid is out. Cell phones, of course, computers, laptops, networking devices, communication devices, GPS units, PlayStation. I don't know what the PlayStation this one is. PlayStation 4, right? So gaming systems, right? These are all examples of digital systems. If we look at just the basic building blocks of a computer, um, what we have, we can classify it into a few basic things. Usually, it's like a computer has some processing, memory, and input output. Right? And there are a couple of different ways. I have two different diagrams to show you. Here it is conceptually with block diagrams. So you have like your central processing unit, in this case like the microprocessor, and you have so-called read-only memory and random access memory. When you're talking about computers, one of the specs that people care about is this random access memory. Okay, input devices and output devices. Um, it could be, like here's some examples of that. Input output is um, your hard drive. Sorry, not hard drive. Keyboard, mouse, camera, whatever. Here's some outputs: monitor, printer, typical ones to use for that, and then the processor in the center. Um, you have some. Additionally, you have some potentially. You might have an output device could be a hard drive, right? Or an input output device could be a hard drive. This might be printer, like I said, printer, monitor, an input device like any of these over here, potentially, or some other. Could be a retinal scanner or a fingerprint scanner or something like that also. And then there's some other application specific circuitry. But this is like the basic model. Typically you see is you have some I/O, input and output, some memory that can't be changed. This is usually like something that the computer has typically to like boot up when it initially boots up. And then the random access memory. And this might be networking devices, right? Connecting to the network, Wi-Fi, or a physical connection on Ethernet, let's say, okay, or Bluetooth, okay? Now, one of the things we could say about computer systems is they have these five things or five operations that they perform: inputting, storing, processing, outputting, controlling. Okay. So all systems have this capability, right? You have to be able to get information into the computer. You have to have a way to save that data or store that data. Typically, this is done like on SSD or hard drive processing. So you have some ability to process information, right? You have programs that go through. It could be like a word processing program or a spreadsheet, gaming program, a GPS program, quite a lot of different things you could have, potentially a drawing program. And you have to have some kind of processing. So your computer performs processing of the information, um, potentially displays some output from that, and then also has the ability to control things, okay? Control some operations. So these are the five basic things that all computers do, okay? And here's another one in terms of the computer architecture. What you'll see is that this is like your central processing unit. It has all this capability and center. And for you, for now, we're just trying to give you kind of an overview. So when we start to talk about specifics, we'll talk about like where they are actually applied. Okay. So here's the CPU, like Intel, like the i9 or i7 or i9 version is pretty popular now. That's the CPU, and you have, of course, the CPU has a lot of capabilities and other modules associated with it. And you have like input and output, and they have a control unit on the CPU, and it's like controlling like the input devices or controlling the access to the information from the input devices, and the same thing for the output. And then it has main memory. So when a computer program runs, it actually gets stored, taken from a secondary storage. That could be input or output over here, secondary storage, and brought in and stored here, and then the program is executed on the CPU. Okay, so this is another basic diagram you'll see for the basic computer architecture. Okay, 1.2, binary numbers. Okay, binary number is basically just a base 2 number system where you have only two symbols, 0 and 1. And that's really essentially, if you break it down into its finest component or drill all the way down in a computer, what you'll find is that they're essentially for each smallest device on the system is that each one can have two states, basically can be on or off state, okay? It's like a light switch or a wall switch, okay? And we also look at like base 8 and base 16 number systems in this class, where base 8 is one way to, if you group 3 bits together, it's a shorthand notation for base 2. And base 16, if you group 4 bits together, it's also shorthand notation for base 2. And what we're familiar, of course, is base 10. Base 10 uses symbols 0 through 9. Base 8 uses 0 through 7. And base 16 uses 0 to 9, then A, B, C, D, E, and F to represent 10 through 15. Okay, since we run out of symbols at 9, we use the first letters of the alphabet for that. Okay, with base 10, you can think about a number like, let's say 25, right? The 2 has a weighting of 1, is essentially 2 times 10 to the 1, right? A weighting of 10, while the 5 and the number 25, base 10, has a weighting of just 1, or 10 to the 0. Well, it works the same way with, with any other base system, right? It's like whatever position, like this could be the position of the bit. This is the rightmost bit, and that has a weighting factor of 1, while the next bit, the next one to the left of that, so if we created a number and a number was, 10 or 100, if it was 100, what we would find is that it's really just equal to, if we convert it over to decimal, it's equal to 4 in decimal. Okay, so this just gives you the weighting of the different bits, starting from the least significant bit or the rightmost bit and going to the left. So if you had a number that had, well, this one has 23 bits. So if you had a number that was 23 binary digits long, the most significant bit would have this value if you convert it over to decimal. This would be the decimal equivalent of that. Okay. And what we'll do is look at some examples of that so you can see that a little bit more. Okay, number-based conversions. This is one of the important things that we'll do initially in this class. And the basic idea is that, we typically deal in base 10 and, computers deal in base 2. So we need to understand that process that the computer performs for it to go from base 2 to base 10 and base 10 to base 2. So if you're interacting with an application, typically you don't put a number in. If you're using a calculator or let's say a word processor, you wouldn't put a number in. A word processor is a little different, but let's say it's a calculator. You wouldn't put the number in as base 2. You put it in as base 10. And then it's up to the computer to go through the process of converting that, or the program to convert that into base 2. And then to store it as a base 2. And then when it's ready to read, you're ready to read that information out of memory, it's a base 2, and it's converted back to base 10 and displayed. Okay, so this is one of the things we're going to look at. We'll look at these number-based conversions. Okay, so basically what I said, all right, computers use base 2, people typically use base 10, all right? So the base really is just defining the number of digits used in that system. Like I said, base 10 has 0 through 9 or 10 digits. And in this case, if we think about just writing it down, the range of it is, if it's base 10, the B here is 10, right? So you go from 0 and this becomes 9. So the range would be 0 to 9. If it's binary, base B is 2. So 2 minus 1, it'd be a 0 and a 1. Okay? So here's example base 10, base 2. And this is also, the other term they use is the radix of the number system, or the base. Okay? Radix is another term that's commonly used. Okay, so if we're looking, talking about like weighting or places, what is the value of the specific places in a number? If you had a number, if you had whatever number you had, to come up with the actual value of that number, you would have to think about its weighting, or the values that are associated with that, right? So you start with the first column. So the least most significant is a 1, has a base of 1, or a weighting of 1, or a place of 1. The next one has a place of 10, 100, 1,000, right? And this is what we would expect. If we were looking for the actual values, at least if you're going to make the conversion to decimal, what you'd find is the first one is 2 to the 0, because the 0 is the location, essentially. This represents the position, right? So this is the least significant bit, or the rightmost bit or digit. This is the next one. This is the next one after that. So it's going from the right to the left, okay? And we'll take a look at some examples to see how that is. All right? So it has a different weighting. Okay, just to show you what I'm talking about, if you go in the textbook, you'll see, like here, if you're talking about really essentially any number, any base system, we can use this example in this base 10, but also any base, it really doesn't matter. But you see a number could be structured like this, with using these A's to represent the actual coefficients. So the actual number that you see. So starting from A to 0, A1, 2, 3, 4, 5, and then if you go, and it keeps going, of course. And then you could also go to the right of the decimal place, and then the notation is using a subscript of the negative numbers. Okay. So, for example, um, if you have a number 7,392, essentially to come up with its actual value, you would just put in, a, you know, this would be the A3, so 10 to the 3 times 7, 10 to the 2 times 3, 10 to the 1 times 9, and 2 times 10 to the 0. Okay? All right. And then if we did the same thing with base 2, so like here, if it was 26.75, so the powers over to the right-hand side are just like, it's times 10 to the minus 1, or 1/10. This is 100th, this is 1,000th. Well, over here, when you're doing base 2, let's say 26.75 is your base 2 number. It's the same idea. Here, what you would see is that starting from, let's see, oh, yeah, we'll go through the process of actually converting it. But you can see from this case, what is this? 1 times 2 to the 4, right? So it's 1 times 2 times 2 times 2 times 2, which is 16, plus 1 times 2 to the 3, which is 8, so there's 24. And then we have 0 times 2 to the 2, because it's 24. Then it's 1 times 2 to the 1, which will give you 26. And then the other value for A to 0 is 0. And I'll show you how you can go through the process of making the conversion, going from base 10 to base 2. And then we have our decimal places, or decimal values, or fractional values in this case. So it's a half plus a quarter. Okay. So that's how the number is structured, right? So this one doesn't show the conversion, but it shows you the number, how it's structured. So basic idea in general, here's the formula, right? For that, for any base system, it doesn't matter. Okay. This is R would be the, whatever value it is, right? So this would be its position, N is position, and R is the radix. Okay. Our base R of the system. Okay. So these are the two examples. This is if it's base 2, and this is if it's base 10. Okay, so if we want to take a look at base 10 to base 2 to start with, this is the process. We start with the base 10 number. We do conversion by repeatedly dividing by 2 and keeping track of the remainders. And then the result of the remainders is the binary number that's associated with it. Okay, so taking a look at an example, let's say that we had 41 as our number, base 10, and we want to convert it to base 2. So you start by doing the division. So you divide by 2, you got 20, and then in this case we have a remainder of 1/2. So 1/2, essentially, it's a remainder of 1. But it would be 20.5, right? This is written a little bit differently. The author wrote it this way, but it's 20.5, so it's a remainder essentially of 1. Okay, how they wrote it as that being 0.5, but you can see how they're doing like a decimal division. Okay, so you check the remainder each time, and if it's a half, essentially what you're saying is the coefficient that you're going to use is 1. All right. So now you have this number. So you keep doing it, you get down to the end until you have your quotient is 0, and you have, in this case, you could have a remainder of, you'll have a remainder of 1, right? If you didn't, you could, or 0, you could have 0 here. So if you got to 0, it would happen sooner, so you wouldn't get to here. So if you have the quotient is 0, and then you'll have a remainder that's left over at the end, the 1. All right. So what you do then is this basically becomes your least significant bit, and this one, the last one, is your most significant bit. Okay. So if you make the conversion, 41 base 10, here's the number with the coefficients. Just this is the most significant bit. I'm sorry, this is the least significant bit, and this is the most significant bit. So here's A5, a 4, 3, 2, 1, a 0. Okay. And you can also go through and, do the same thing if you wanted to. Like here's an example. You could actually do, this one doesn't show it, but this is basically 153 and then dividing by 8 and then keeping the remainder. And it's a good example to see this come out. Divided by 8, and then this 153 base 10 would be equivalent to 231 base 8. It's a good example to try that and do that. Okay. Now, if we're going the other direction, base 2 to base 10, we list the digits in order horizontally to appear in the number. Then we multiply each one by 1 times 2 to the n, where n is the place of the binary digit. Add all these numbers to come up with the decimal equivalent. Okay. So here, let's say, this should be subscript. I'll have to correct that. This is a subscript here of 2. It didn't come out right on the slide. But this is 1001100101 base 2. So if it starts off, if there's 9 digits here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 digits. The first one is 2 to the 8th, then 2 to the 7th, 2 to the 6th, 2 to the 5, 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0. So you just multiply each of those numbers by their weighting value or place value, and then you come up with the number. So you perform the multiplication and addition, the arithmetic associated with it, and the end result is 357 base 10. Okay. Now, fractional components, in this case, what you would do is so when you're dealing with a fractional number, let's say it's 0.6875, what you do is you can multiply it times 2 and come up with the integer. The integer value will be your coefficient, and then you have a fractional component. So in this case, let's say that our fractional component is 0.6875. You multiply it times 2. You keep the integer. The integer is either going to be 1 or 0 when you go through and perform these operations. And you have a fractional component. So this times 2 is integer and a fraction. So the fraction gets carried down, and you do the same operation again. And the integer component becomes your coefficient. Okay? So we perform this operation, in this case 4 times. Keep doing it. Like this is times 2 is 1.5. So here's the integer, and here's the fractional component. And when we get to the end, when our fractional component is 0. And so in this case, to represent 0.6875 just becomes, let's say 0.1011. Okay? Now you can perform the same, you could do the same operations with like base 8, base 16, whatever base you want, right? So like in this case, you multiply it times its radix or its base. And in this case, we go down. And you'll see the coefficients here, 4, 0, 6, 5, 1, 7. Okay. And what you notice here is even though how many digits we've gone through 6 digits, we still have a fractional component. So we'd have to continue along further. And at some point, it may turn out that it's just going to be an estimate. But this is like the final result would be, 0.4065517. Depending upon how many digits, you could keep going further and further. And this is an example in the book. This is the example from the book. This is just like a truncated version of that. Okay, octal and hexadecimal number systems. Okay, like I said, so far we looked at binary, and we looked at binary or base 2 and base 10, right? Because we're familiar with base 10. So octal number, base 8, has a range 0 to 7. Hexadecimal number has a range 0 to F, because we run out of symbols after going 0 to 9. And what we find is that like there's shorthand or useful conversions between binary and octal. Okay, so But a single octal digit uses to replace three binary digits, and a hexadecimal is used to replace four binary digits. Okay, so if we look at the table very briefly, what we can see is the equivalent values for those. So let's say this is base 10. You have a number going all the way up to 15, right? So what do you expect? This one is going to be F, right? If we were to do a base 2, we just count 1, then you have 1, 0 because you ran out of digits, right? So you carry one over. So it's just like counting in any base, right? You run out of digits. In this case, you'd run out of 9, then you have to carry one over. So each time you only have one digit, so you go, or two digits, you have a 0. The next time it's a 1. Now when you add a 1 to this, you get a 0, carry a 1, 0, carry a 1, and you keep counting like this. And what you would notice is that if you're making the direct conversion between binary and decimal, this has a weighting of 0. This has a weighting of 1. This has a weighting of 2. So if you were to do the conversion, it would be 1 times 2 to the 2. And there's your 4. And then this one would be 5. So you can do the base 10, base 2, base 10 conversion and see that these are equivalent. Okay. So if you keep counting, and one of the things you're going to recognize here, if you take the first 3 bits, the least significant bits, you run out of digits here, or run out of symbols here, right? And you got to carry one over. So here's 3 that runs out of it. It's at the same point that the base 8 number runs out of symbols. Okay? So what you'll find is that you can do groupings. So if you wanted to convert a number directly, all you have to do is group them in groups of 3. And actually this example down here shows that is the case. Okay? So like here's a number, and you want to convert this to decimal, or sorry, this is base 8, so they're making a conversion to base 8 here, and then this one is base 8 to binary. And here's a base 2 to base 16, base 16 to base 2. Okay, so you can see the process here, and there's examples in the book that also go through that. But the basic idea, you'll notice, the key point here is the grouping is done with 3 digits. And the most significant digit, you just put a 0 on the end. So anything to make it even multiples of either 3 or 4, you would put a 0 over here. Okay. So you could go through and make that conversion. And it's pretty easy if you wanted to go to base 8. Okay. Going from base, so to base 8, it's just grouping by 3. Okay. And then this case, you'll see same thing. Now it goes in the other direction. It goes from base 8 to base 2. Then this one is now a grouping of 4. Okay, so you just start with the binary. You take 4 digits starting from the right, at least left of the decimal point, of course, first. Then starting from the right, grouping of 4, 4, 4, and then in this case you just add 2 zeros to the end. Okay, pad it with 2 zeros, and then you go to the right from the decimal point. So you're going like start at decimal point, you go to the left, then you go to the right. And the first one would be just F. So 4 ones, group them in 4, and then the next one, group of 4. Okay? And the same thing, you can pad it to the right. So that was just a 2. So making conversion pretty straightforward between these. And then the same thing over here. This is going in the other direction. This is going from base 16 to base 2. Okay? And that's pretty much it for going between octal and hexadecimal number, or in this case, we're going between the different bases of the number systems. So you can take a look at some of the examples in the text to see that done. But that's the basic process. So up to this point, we looked at all the base 2, base 10, base 8, base 16, and the conversions between them. And what we found is, base 2 is because computers work in base 2. Base 8 because base 8 is a nice grouping, a shorthand notation, a way to group 3 bits to make it easier to view and look to visualize it. And base 16 is 4 bits. So base 16 is actually more common because it works out better in blocks of 4 than in blocks of 3 for base 8. right? So the really key ones are like you'll see base 10, base 2, and base 16. Okay, and that's about it for up through section 1.4.